Hello, I'm excited to present this brief live demo of our new metastructure generation system and walk through generating this optimized component. Now with tapered struts, which is pretty exciting, and field-based meta optimization, so you can see that the struts are being adapted to field-based data. In this short workflow, I'll go through our new hyperstructure generation process and also describe how, working with our new partner NAVASTO, we can now generate unlimited multi-parameter large AI training datasets organized for latest AI optimization control strategies. I'll switch to the coding window where you can see our main control code on the left here and then numerous subprograms supporting this process on the right. We've developed a series of 8 modules in Python and C++ that execute in series. And program execution is controlled by the master program. And for now, we enter our parameters, structural and material parameters and boundary conditions directly in the code, but a Blender add-on GUI is in the works. First, we want to import the shape. In the previous demo, I demonstrated this operation on a rectangular beam with a hole in it. And we showed how the optimization, if we apply a load to the center of this beam, we get this, an optimized structure. Again, fixed on the ends and loaded in the center so you can see how it varies. But I thought this time it would be interesting to look at a more complex shape. So let's open that shape, and it starts out as an STL file. Here we go. And now we have the component loaded in. And this component is obviously much more complex than the simple rectangle. And we're going to apply our hyperstructure generation system. It has sharp edge features and curves and holes, so it's multiply connected. We have to keep this shaft connector end piece here. So I've just used a simple Boolean to segment that part from the body. That segment gets automatically reattached later. First, we need to set some necessary boundary conditions. So you can see here we have two planes here for the fixed boundary conditions, or it's fixed. This component's fixed at the ends where it connects to the rail underneath. And then we also have this cylindrical surface where loads are applied, combinations of Z, Y, and X loads to the end connector. Mostly Z and Y because that's our prominent loading configuration for this component. We have a basic idea of what the loads and material properties of the component are, so we preset them here in our auto-generator code. The main code executes 8 subcode steps in sequence. For brevity, I'll summarize. The first 4 steps, here's the switches for the steps, generate the initial wireframe networks with controlled density and performs all of the finite element analyses for every defined boundary and loading condition, fully automatically. The next 3 steps map the field data from the FEA to the network data, computing the edge and vertex thicknesses based upon whatever stress fields we want. And in this case, we're mapping to the von Mises stress magnitude field because we want to meta-optimize this component for strength. But we can map to any computed field, so we could have a heat transfer optimization as well. The final step generates arrays of new hyperstructures that are structurally adapted to the fields computed in the earlier steps. From that array, we select the best performing components based upon whatever criteria we define and repeat this process until an optimal component's achieved. So this is pretty interesting because from one hyperstructure generation run, you not only get fantastic optimized hypercomponents, but also a full set of data for AI training, which I think is extremely interesting. Imagine this, every component and every shape that we make, it's added to a training data set, which will increase the power and flexibility of the AI. Thus, it's a self-perpetuating system. The AI can learn from itself. We're right now computing all kinds of simple and complex shapes for the database. And please contact us if you have any questions or for more info on our new AI work. So I'll go ahead and compute the first steps now. I think I'll switch back to the modeling window. We have our code over here, so since I've already set all the parameters, all we have to do now is hit the run button. So I'll go ahead and hit the run button. And off it goes. We can monitor the progress in our command line window. And it takes a minute, but it's gotten much faster than it was just a few months ago. We're taking advantage of NanoVDB to do the volumetrics now, which has speeded up the process by approximately 100 times. So it's almost done. And all done. And here I've just loaded in the data we computed. So we have all of the control point data for vertices and edges of this network structure. And I will just turn off this so that we can see inside a little bit better. And there we go. So now we can see how the network is generated for this component. It's important to notice that the network is very well conforming to the edges and curved surfaces of this structure. Now we'll generate the hyperstructure for this component. I'll switch over to the main window and we'll generate a series of Hgon hyperstructures. In this case, we are running 8 boundary conditions, so we'll get 8 manifold hyperstructures. And this takes about 4 minutes and to do all of the analysis. I'll note that we only really need to do 2 boundary conditions for this component, but we run the full set anyway for the AI training. And here's our initial results. So this is great. This is a uniform hyperstructure. We always do a uniform structure first to make sure that our boundary conditions and things are suitable. And it looks very good, very conforming and nicely distributed metastructure network. Let's pull up the finite element field data for this structure and see what we have for optimization. This is the volumetric field data that we just computed for this structure, and this is for bending loading, in other words, in just the Z direction. And you can see how we get some stress concentrations here, and we get a stress field. This is von Mises stressing in. So I think it's exciting to let's see how our optimization worked. And here it is. Okay, so this is our field optimized structure. So you can see that the thickness of the struts is mapped to the volumetric field density. So this is for the Z direction. Let's take a look at what happens when we load it in the X direction and see what kind of pattern developed. We'll switch to the Y direction loading field. It looks sort of like that. Much different, obviously. And here is the hyperstructure now adapted to a Y-axis loading field. And as you can see, the pattern follows. So it's much different than the previous pattern. And we get the thicker struts in these regions. It's exactly what we want. I'll mention again that these are all fully manifold, automatically generated structures. I'll take a second here to mention our new tapered and contoured struts, which dramatically improve the continuity of the generated hyperstructure. I'm pretty sure that no other company or group can do this. We can control our strut shapes now any way we want. We can make elliptical struts with axes oriented to flow or temperature fields, and that's pretty exciting. The excitement continues because we can combine fields. For instance, here's the result for a combined Z and Y hyperstructure. So we get strengthening still at these regions, but also a little less strengthening here because that's following the other field. So in this way, we can recombine fields in the next optimization step and continue selection of which field and which combination provides an optimal shape. We can generate fields for each step. So the variations are potentially endless, especially since we can achieve manifold structures for every result. That's where the AI comes in. I hope that makes some sense. So that's about it for this brief walkthrough. We've shown how we can generate hyperstructures from base systems and then optimize them with various different field strategies. Thanks for watching, and if you have any further questions or want more information about our hyperstructure generation capabilities, feel free to visit our webpage and contact us. We respond.